Welcome to the Art and Design of Computer Programs. This series hopefully will introduce you to the ideas of programming, the theory of computation, how computers work, and why they work the way that they do. This is based off of the famous Structures and Interpretation series published by MIT in the 1980s for Hewlett-Packard, HP employees back during that time. I always appreciated the idea of connecting wizardry to computers because for many people, wizardry and programming might be very similar. It feels ethereal and enigmatic, ineffable in a lot of ways. And the truth is, programming and learning how to program and learning the concepts in tech are not as ineffable or unreachable as one might think. Learning how to program is just learning how to think in logic and in systems. It's learning how to think mathematically. And on top of that, there's some really interesting concepts that come from choosing to learn how to program in the proper way. There is a shocking and growing amount of tech illiteracy in the modern day, especially with the rise and advent of AI. Students are more likely to use these resources without knowing the why behind the what. And I hope to introduce to you those ideas. In this video today, we're gonna talk about the history of computer science and the history of computers, what a computer is, and what programming actually is. Then we're going to have an overview of the whole series as an overall thing, and then we're going to talk about what we're going to do next in the next video. Now first, a little bit about me. And of course, that is a picture of me. Yes, I do look like that, and yes, I do wear a wizard hat. I am a former computer science teacher, and I used to teach high school students computer science. But before that, I actually have a degree in communications and communication studies. I've always had a penchant and love for programming. I also have a love for visual media, as my old visual media teacher would tell you. But I have been programming since I was a kid. I first started programming back in 2008 when my dad first started teaching me. I had an interest in what he was doing at his work at the time, and eventually it got shuffled onto me. I would go on to learn Java and be a part of what is called the UIL computer science team, and that was a lot of fun for me. But I didn't think I was capable enough in order to be a computer science major and thus a software engineer. However, as of right now, I am a software developer, and I've been a software developer for about 3 years. And having been in the field and in the industry and having previously taught computer science to students, these ideas and concepts can sometimes feel difficult to grasp, and I don't blame people for not feeling like they belong in this field. And I also hope to prove with this series that you can have both. You can enjoy art and humanities and history and have a degree in those things, take that expertise and experience, and then learn how to become a software engineer or study something hard, for example, like science or math or engineering. Now, the languages that I use two in particular professionally, C#, .NET, and ABAP. And ABAP is a business language that's used on the SAP system for business development. I think it's a fascinating language, but at home, I like to use C or Go. Sometimes I'll dabble in Java, but really not so much anymore, but I do love C, and C is one of my favorite languages. It takes some time to learn it because you do have to understand how to manage memory manually, and we'll talk about that in a different video. I think there's a lot of hate for different languages. I think they're all pretty neat in their own way. And then, of course, professionally, I do use SQL, which is a database querying language. And before we begin our discussion about what programming is, I want you to think about mythology and history and our connection to light. If you look back at mythological texts or historical texts, you'll see that people had a keen interest in fire. Our mythology stories, our founding stories, for example, Moses and the burning bush. On top of that, at the same time, you have the Egyptian concepts of light. If you pay attention to these stories, they're all going to have their own separate respective stories in regards to light and to fire. And I want to talk about fire just a bit. We often think of fire as one of the defining features of what made humans humans. It changed us permanently. And in the same respect, I would say that technology has done the same exact thing. The question is whether or not technology will make us better or worse, and people debate about that all the time. But what we do know is that just as fire changed humans for good, technology has also allowed us to make significant advances. And also like fire, the inverse of light is our darkness, our night. And computers deal with these binaries, day and night, evil and good, ones and zeros. We call these ones and zeros bits, and a 8-group package of these bits, bytes. And it was this structure, these bits and bytes, these are the foundations of the things that we use. They're very easy to understand. Once we get to know them, they might feel almost as ethereal as the founding stories that we come to believe and even worship. And so we're going to look at programming from two perspectives. Programming as a literal, imperative, and command-based experience. The physical things that you see. I'm going to crack open this computer that I use to record, and I'm going to show you the parts of the computer. You're going to learn all of these literal things that I deal with on a daily basis in thinking about systems and the physical systems. Programming is more than just the literal and imperative and command-based experience. It's also esoteric in a lot of respects. Many of the languages that we talk about today bear this esotericism to them. They're abstract and almost near mystical. One of the languages we'll look at is called Lisp, and we'll learn how to build a thing that lets us compile or turn into machine code. The Lisp's called an interpreter, really, but we'll talk about things like time and space complexity, computational theory, complexity theory, functional behavior and analysis, language theory eventually way down the road, and it's going to feel very esoteric. We'll talk about undecidability problems. This is all pure mathematics. These are things that are just in our heads. You can't physically touch them, but they're there and they exist. We'll learn how to do all of that. We're just going to focus first on this programming as a literal, imperative, and command-based experience. And to start us off on our discussion about the computer, we have to know where it came from. And I want you to pay attention to this gentleman right here. His name is Charles Babbage, and he created the very first computer, so to speak, the Babbage engine. It was supposed to be a computator and to support the loom industry, which was very big at the time during the Industrial Revolution. And he began to design a fully functioning system. And this woman named Ada Lovelace, she has a whole programming language named after her. She became the first computer scientist, the first programmer. She wrote the first algorithms to go in conjunction with a computing machine. And I think that's really fascinating, honestly, because we were doing this in the 1800s, and it only got better. Because you see, we have these two fine gentlemen here. Sadly, this is Alan Turing. Sadly, he passed away way too young. It is a real shame what happened to him. You've probably seen the movie about him called The Imitation Game. Alan Turing was no slouch. By the 1930s, we had electricity, and we really began to understand that we totally could build computational machines. But the question was how, and were they even theoretically possible? And so in 1936, mathematician Alan Turing and his mentor, Alonzo Church, were trying to solve the same problem, also known as the halting problem. And they had this question, which was, given a function, a mathematical function, with an infinite number of inputs, can we tell if we're ever going to have a solution? And what Turing came up with was, let me dream of this machine, this magical machine that can solve my problems. And he wrote it down in his paper, but he said, let me invent this machine mathematically that can solve these problems. And I know that it'll solve the problem when it stops, when it finishes, when it produces an output. Because remember, a mathematical function takes in an input and pushes out an output. And I want to pretend that there's a machine out there that exists that can do that. And we call these machines Turing machines, and every computer is based off of his idea, this Turing machine. And at the same time, his mentor, Alonzo Church, was approaching it from the other direction, from the pure math perspective. He thought, let me invent a mathematical style for writing out functions so that we can have this language of computability. We call it lambda calculus. We're not going to learn it right now, okay? We're not going to talk about lambda calculus quite yet. It's kind of crazy. But his ideas would go on to become the foundations for some of our earliest programming languages, and their theses got merged together into one thesis, the Church-Turing thesis. These gentlemen invented the idea of the modern field of computer science. After the Second World War, we began to actually build these machines in earnest. And the first two women who were really heavily involved in designing and developing the languages and education of these systems was the Commodore, Dr. Grace Hopper, and Sister Mary Kelly. Now, Dr. Grace Hopper was a brilliant scientist in her own right. Sadly, she has since passed away. But she invented the first business-oriented programming language called COBOL. And my programming language that I use, ABOP, is based off of COBOL. Meanwhile, Sister Mary Kelly, a Catholic nun, became the first true educator in computer science, and she had a deep love for the thinking machine, so to speak. And she was phenomenal at it too, and deserves just as much respect as Dr. Hopper does. And then we start to slide into the modern era in the 1970s. These two gentlemen invented the programming language you and I will be using, the C programming language. These gentlemen are rock stars in the computer science world. They invented one of the most important programming languages on the face of this earth. They are phenomenal, amazing. Dennis Ritchie here has since passed away, and I believe Ken Thompson is still with us. He works for Google on the Go programming language. But it is a beautiful, wonderful programming language that was built to be with systems in mind, very low-level things. And it is the foundation for every system that we use today. This language that these two gentlemen helped build at Bell Telephone Laboratories in New Jersey changed everything. And so that's kind of the really, really short overview of the computer and the direction the computer went. But as you also know, throughout time, they've gotten smaller and smaller and smaller and smaller, and now they are little tiny things you can hold in your hand, and we can do all sorts of crazy stuff with them. But what is a computer? Well, deep down, a computer is any machine that can be programmed to carry out arithmetic operations in a step-by-step manner. And these step-by-step things are called algorithms. These instructions can be saved to permanent storage along with the data that is operated on. They can be called and run in order to perform specific actions, and these instructions that are saved are called programs. Computers generally have a way to perform arithmetic, a CPU, a way to temporarily store working data, RAM, a way to permanently store data, your hard drive or your hard disk, ways to display, manipulate, and read data, so your screens, your keyboards, your mice, your speakers, and a way to hook all of these parts and peripherals up together, your motherboard. Typically, so the CPU, we're going to talk about all the parts now. Typically, your CPU is the part of the computer that does all of the core calculations, so it handles all of the math. And the kind of math it does is not complex math. Well, it is complex math. Addition, subtraction, multiplication, and division on the strings of ones and zeros, those bits and bytes. And it takes in those bytes, performs the addition, the subtraction, the multiplication, the division, and then it spits them back out to the RAM based on what the machine code, the program that you've written, the instruction set language that you've told it to do, the instructions you've given it to it. It's the compute part of the computer. And we're not going to worry about how it works just quite yet deep down. We're not going to dig into that quite yet, but we're going to want to know just the very basics of how it functions eventually. But for right now, just know that this is the processor. This is the machine, the brain of the machine. And we'll learn more about how the brain works. But we need also to store data temporarily, these bits and these bytes. Welcome to the random access memory. As you know, there's a wonderful Daft Punk album of the same name. It holds all of our temporary working data that you need while the computer is awake. And at the time I've written this, there's a shortage of hard disks and RAM. And so there's a lot of discussion in the tech industry of how is this going to impact us, which is why I think C is such a great language and why we're going to be using it. And there's two sides to the RAM. There's going to be the stack and the heap, and they're both kind of out there. They're ethereal. We'll talk more about the stack and heap later, but the RAM physically stores each byte of data in a thing called an address. And this will be very important later because we're going to learn how to access the address, and we're going to learn how to access the data from each address as needed. But it just stores bytes at specific addresses, and you can get that byte based on the address. Next, we want to store data temporarily, and that's going to be our hard drive. And there's two kinds of hard drives. There's HDDs and SDDs. And HDDs, hard disk drives, are older. I remember playing around with hard disk drives, and my dad said, "Don't open it up because you're going to point the laser dry and you're going to never be able to see again." Well, it uses a laser to read the data off of these physical platters right here. And you can't see them, but there's the platters right there. And you can hold more data and for longer term, but you have to be careful with them because there's a moving part. This little arm here moves very quickly, and this thing spins very fast. And so you have to kind of be gentle with it or you can break it. Now, solid state drives, which I don't have a picture of, They're newer, they're faster, they can hold less because they're more expensive, more pricey, but they're faster. They're so much faster, and theoretically you don't have to be as careful, but they're just so darn quick. They also don't last as long. Hard disk drives can last for a very long time if you're careful with them. SSDs, eventually it'll do something called bit rot. It's going to lose bits over time, and then the data is going to become corrupted. And that's not necessarily what you want. So you kind of have to think about preservation over time. Next is the GPU. Now the GPU is very special. It is more new compared to all the rest of these, but the graphics processing unit is similar to the CPU in that it does computation, but it's meant to do computation for one specific thing: linear algebra and matrix multiplication. And you will eventually, at some point on this channel, learn how to do linear algebra, because linear algebra is a core feature of modern programming, but it's optimized for doing matrix multiplication. But they're big, they're beefy, and they have been expensive for quite some time thanks to cryptocurrency farms. And so they can be hard to find in some ways. There's lots of jokes out there about the things you do for a good GPU. Next up is cooling and power. Now all of this creates a lot of heat. And when you have a big beefy system, you want to have it be nice and cold, because then that means your machine's going to work a lot more efficiently. And so we have to have power and cooling. You might be able to hear the fan of my laptop going off like crazy in the background, because this computer is 10 years old, so it's chugging along at this point. But there's different kinds of power and cooling, as you can have battery-based systems, a corded system, you can have fan-cooled, water-cooled, a combo of them. Usually there's a combo. There's almost always what's called a heat sink, and that's going to be these little fins coming off of it right here. That's a heat sink. And then the room environment and space considerations. So if you've ever worked in a server farm, those rooms can get really hot if you're not careful. And so you want to make sure you're cooling down those rooms quite well. And then finally, for the parts, we have the peripherals. We have the monitor, the keyboard, the mice, the speakers, all of this stuff that allows you to see what's going on. Back in the day, it was just a printed readout that would print things out, and you'd use punch cards. Well, then somebody invented the keyboard and the digital monitor, and that was pretty nifty. And now we have all these really cool displays. We're going to take it kind of back to simplicity pretty early on, just so that we're not kind of overwhelming ourselves with all of this stuff. We're just keeping it nice and simple and old school. And all of these peripherals connect to the computer's operating system via drivers. And so now that we know what a computer is, and almost every single computer we use has some sort of all of these features, including your phone's got a touch screen, we have to ask ourselves this question. If those are all the parts of the computer, what is programming? When we say we program, what do we actually mean? And so I want us to think of programming as being a wizard. Wizards create and name spells that they can then cast later. And procedures are like the named spells, that once you've written it down and you have the tools necessary to cast the spell, you can then cast them at a later date. And processes are the actions and the rituals required in order to cast that spell. So for example, I have this wizard, this very evil wizard here, who's going to be dropping nuclear annihilation upon William Defoe, and he's cast the spell in order to drop said nuclear annihilation. Now he might be a little close, he might get vaporized too, he's going to get Hiroshima if he's not careful. You know what I mean, you get the idea. And we worry about building these procedures and these processes in programming, and we have a different name for procedures. We can call procedures routines, we can call them functions, we can call them methods, and a procedure, also called a function, is just a named reusable spell. Once you write it down, once you've created it, you can cast it 1,000 times, so long as you have the right components necessary to cast it. And we're gonna talk about procedures in their own special subcourse eventually. We're also gonna have our own lecture on what a function is, but just know that procedures are really important. We talk about procedures all the time. They're the spells. So first off, you've got your magical concept, which is defining the spell. And that can be thought of as defining the function. Then you have casting the spell. So you say the spell's name to invoke it, which is the same as calling the function. You're writing the function down, you're calling it in some way. And then you have your spell components, which are the different spells bits that are required. So if you play D&D, you know that some spells require that you have a long rest, or you need a diamond, or you need the blood of a goat or something, I don't know. And you can call these function arguments. We call them parameters. You have different inputs. By taking in the different inputs and casting the spell, you then have an output of some kind. Goodbye, William Defoe. No, so here's an example I wrote down. Obviously, I'm not the world's greatest drawer. I'm not an artist by any means. So here he is writing down the spell. So he's creating the spell. He's initializing it. And then he's casting it. But oh, well, haha, he's actually just drinking Fireball whiskey. Tee-hee. The guy's confused over here. It's a really stupid joke. And then you can think of the processes as your programs. And you can think of it as a ritual. And the ritual I have here on the side, and not, again, this is not an endorsement or promotion of any particular belief or faith. You can think of going to mass or whatever religion you grew up in or participate in. There's going to be rituals in all of those religions. A ritual is just an ordered sequence of steps. So if you've ever been to a Catholic church or an Anglican church or an Orthodox church, you walk in and the service starts and everybody stands up. And then they go forward, the priest and the acolytes come forward down the aisle, and depending on what tradition you're a part of, you might do different things. And the priest is going to say some words in the opening, you're going to recite things together, and then you sit down and you listen to the scriptures being read, and then you stand up again, you say some more stuff, and then you kneel, and then you sit, stand, kneel, sit down, kneel, sit, you know how it is. But every religion has these, and have rituals in our own life. And we think of rituals as an ordered sequence of steps that unfold over time, with each step building upon the last. And in programming, this is a process, a sequence of operations that run from start to finish. They take our inputs and transform our into outputs. So we have an input. Whenever I get up, you have me, groggy and sleepy, and I apply getting my clothes on, getting my hair brushed, getting my teeth cleaned and my body cleaned. And my output is I'm awake-ish and I'm clean now. And that's the output. And what's super fun about this is we can actually have multiple processes running at once, and this is called concurrency. We'll talk about that in this series later. Processes are a collection of these so-called spells running in an ordered sequence of steps. And when it comes to processes and programs, order matters with both. You cannot verify a password before you've submitted it. You can't cast Fireball before you have invoked it. Steps have to have a natural order and must be followed to prevent unwanted behavior. If you've ever watched Mystery Science Theater 3000, there's an episode where they make fun of the movie Sampo. And there's a line in this particular thing that's where Mike Nelson goes, "You put your feather in before the wool?" Because they're joking about the processes of getting what's called the Sampo, which is from Finnish mythology. I was put that in here because it's a joke about processes. Order matters in everything that you do in programming. And another thing we can think of when we think about processes and procedures is we can call the collection of these things algorithms. And algorithms are the mathematical step-by-step instructions in order to complete a certain task. So an algorithm for a morning routine would be waking up, turning off the alarm, getting out of bed, taking a shower, getting dressed, so on and so forth. I wouldn't want to get dressed before I take a shower, and I wouldn't want to take a shower before I've gotten out of bed. And we talk about algorithms in the sense of how to complete certain mathematical things or certain behaviors or logic. And we'll get more into algorithms. They'll have their own special dedicated section in this series. So for example, I want you to grab a piece of paper and a pencil and a friend, if you have a friend, and if you don't, you can do it for yourself. And I want you to teach somebody how to draw a house. So go on and pause this video and teach somebody how to draw a house. And ask that person or yourself, be a butthole with me about this. You know, if I say draw a square, you say how big. If I say draw a triangle, you say what size and what shape. Because if you think about it, if you aren't specific, somebody might mess up. And you can think of that as being like a computer. Computers will always do exactly what you tell them to. Period. End of story. So we have to be specific when we talk to a computer every single time. And that's where people tend to get got. They don't think they have to have that kind of detail, but that's the hardest part. And this is because computers are exactly literal. If you tell them to do something, depending on the design of the language and the design of the system, it will do it. Unexpected behavior is possible depending on the language. Sometimes you can have unexpected or unknown consequences when you write these programs, and these side effects can kill people or blow up your billion-dollar rocket. In this case, it blew up a billion-dollar rocket. Something called a buffer overflow happened because somebody miswrote code, and as a result, Ariana 5 blew up. Kablooey! It was gone. No more Ariana 5, and they had to start over from scratch. Kind of stinks. Really sucks. So they had to go back to the drawing board with the program and go, here's the bug, and they fixed it. People died as a result of this one. The TADOCP 25, again, a buffer overflow, which caused a counter to be reset to 0, meaning somebody got irradiated, they got cooked by radiation a little bit too long, and they perished. It was caused by a buffer overflow, a programming error. And you have to be careful when you write code to avoid those kinds of errors. And that's exactly what we're going to be doing with this series. So in the first part of this series, we're going to learn our beautiful programming language C. Now I picked C because C is incredibly difficult and incredibly simple at the exact same time. We're going to get familiar with C, we're going to learn the data structures and the algorithms, and we're going to build a ton of stuff. After that, we're going to learn systems and services. We're going to learn how the computer actually works, how it was written and designed, and the theory behind its design. We're going to learn all the ins and outs of our computer, and we're going to build a lot more stuff. After we do that, we're going to learn about the why behind the what. We're going to get so dingly dang good at thinking mathematically, you won't even have to think about it. You'll just be thinking like a mathematician. I'm kidding. Maybe I'm exaggerating a bit, but we are going to learn how to think mathematically, and we're going to learn why is it this way? Why did Alan Turing do what he did? Why did Alonzo Church do what he did? What did Chris mean when he said Turing machine and lambda calculus? Which is a fair question. We're going to get there. And so in our next video, we're going to talk about the history of C. We're going to install our development environment, aka how we actually build a program. And then in the video after that, we're going to build our first program. And then we're going to start introducing the core ideas that come with writing code. So give me a couple more videos on this introduction and allow yourself to learn. It's going to be a lot of fun. We're going to get there. Catch you guys in the next video.